Hello everyone, my name is Eren Kerimoğlu. I'm a second year, second term student in Bilkent University. My department is computer science. Today I'm gonna introduce you my physics 102 project. My project is investigation of factors influencing induced electromotive force. To summarize my experiment and explain what I did in my experiment, I can say basically I explored how the magnitude of the induced electromotive force in a coil depends on several changing conditions of the circuit by altering certain properties such as the number of wire turns, the motion speed of a magnet, and the type of wire material, and repeating the procedure systematically, we will determine which parameters most strongly influence the induced EMF and how these effects agree with Faraday's and Lenz's law. For further investigation, I'm gonna proceed with my data, my report, and my pictures and videos from exact lab experiment. Alright everyone, here are some pictures and videos from the lab experiment. Before I show you the data, I want to introduce the pictures and videos so you can relate with what I did in the lab. This is here the multimeter that I used to see what volt we got. Actually it was millivolt and it take the peak value. This is the setup generally, and this one we didn't use actually because it was seemingly not uniform pretty well. This is how we tested our magnet, and the magnetic field was also non-uniform. It was giving different values all around the magnet. Alright, this is the video of what we did and how we altered the different factors of EMF. Here is a video that shows. Alright, this is how I did the experiment. By ruler I checked the height and I altered the height. The height altered the velocity of the magnet going through the circuit and everything. This connected to the multimeter here. By altering the height, I altered the volume, and the volume affects the rate of change in the magnetic flux. And here we got different number of terms. Let me show you them also. These are also several videos from different heights: 3 centimeter, 5 centimeter, and 7 centimeter. And here is the number of turns. This one got 200, the other one got 400, and the last one got 800. This is how I connected the multimeter to it. That these ones got special connection points. And this is the full circuit actually right here. I connected multimeter here, and this one was the multimeter was set to show the peak value. The change in the volt, we saw the peak value in the waveform. Alright, now I'm gonna show you my data. Before my data, I'm gonna show you the formulas that I used. Here is the electromotive force, and here is number of turns and change in the magnetic flux by time. The other formula for calculating the magnetic flux, which we didn't actually use because the area and the magnetic field magnitude, actually the magnet's field was not changing. Since I showed you how I did it, here are some data from the lab I got with different turns, with different materials, and with different speeds. Alright, first let me tell you, I did it for 3 centimeter, 5 centimeter, and 7 centimeter of height, the drop of the magnet, and I did all these 3 heights for all that 3, 200, 400, and 800 number of terms. And here is the best data for linearity, of course, I get for this one is for 5 centimeter, right? Yeah, 5 centimeter drop. And as you know, the material shouldn't affect the electromotive force magnitude, the R volt value, and it didn't actually that much affected the final value. These small defections are caused by the resistance of different materials that I'm gonna explain in my conclusion. Alright, in the last table that shows the change in the speed and how I calculated it, it is simple. We learned in physics 101 the formula here. I calculated the speed by using the height of the magnet, 3 centimeter, 5 centimeter, and 7 centimeter of the drops. And let me show you my graphs. Alright, this red line here shows the perfect linearity, the expected results, and the blue dots are my results actually. So what are the percentage of errors? My fixed point is this here, and my error rate is 8% and 8.5% for the other two dots. Rather than proving the formula by the actual values, I compared my data to show the linearity and the results of my lab. Alright, here is my second table that shows the different materials results, and this one got even less than 1% of error rate. These are pretty same. And my last graph shows the speed. Normally the rate of change is related with the speed and should be proportional to the change in speed, but for small drops it was perfect, but for 7 centimeter drop it was something like 39%, as I remember right. Yeah, it was a pretty huge percent of error because compared to the other two. This one generally caused by the off-axis drops and not centralized because I dropped the magnet by hand, and also there was some defections in the multimeter, I guess, because it the peak of the waveform was not calculated pretty well in the multimeter, I guess, because when you do the same experiment again and again from the same height, it would give different result in every trial. So what I did was I did try the drop for 5 times and I got the average value, which you see here. This was the average of 5 drops. It still didn't pretty much fine. Here is my conclusion, which I discussed what could be and what actually are the reasons for those percentage of errors. Is pretty specific error, and I categorize them. The material caused random and systematical errors here, and that's pretty much it. Thank you for listening me. Have a nice day.